The clouds are white because you have two different materials with different refractive index right next to each other. So that's why you get something called scattering. And Mie scattering explicitly actually predicts the way that spherical particles actually scatter the light. So in our recent work that is published in ACS Photonics, Tyndall windows, we're actually trying to modulate this type of scattering. So we are trying to modulate basically how white, a cloud would be in a medium. And let's say instead of using air and using water, we're using liquids and solids. So if the air, for example, had exactly the same refractive index as water, then you wouldn't see clouds, right? And that's exactly what happens if you have, for example, glass particles in a liquid that have matching refractive index. So it's very difficult to actually find materials in a different phases. I mean, like solid phase and the liquid phase that have exactly like a matching refractive index down to the 10th digit, right? But what's interesting is that the behavior of the refractive index in different phases of matter is very different. So for example, if you heat up a liquid or if you heat up a solid, the way and the speed that the refractive index changes is dramatically different. And this is exactly what has not been used for photonic devices very much. So we are trying to basically use that much more with introducing this work of Tyndall windows. So in Tyndall windows, what we are using is basically disordered or irregular set of particles in a liquid host. And these two materials have, let's say, we chose them to have a matching refractive index, not exactly matching, but close. So what happens when we heat it up, or change the temperature, for example, you will see that there's a very sharp peak of transparency as expected, and also can be predicted by Mie theory. You can see a sharp peak in the transparency of the whole mixture, because as the refractive index are matching more and more, you get less and less scattering. Now, what's interesting, or what we found, was that the sharpness of this peak is orders of magnitude actually more. So the peak is basically much more sharper than what Mie theory predicts. And the reason for that, we believe, is that the particles that we use are irregular particles and not exactly Mie particles. They are something called Tyndall particles, or basically, as I mentioned, they're irregular. And for this, we have to use actually numerical simulations to see that why this sharpness happens. How does the roughness and the packaging of the particles actually help to this enhanced scattering? So I think this is a very interesting direction for a whole new class of photonic devices that try to use this kind of dichotomy, or I don't know what is the exact word, but this notable difference of refractive index behavior to the environmental parameters at different states. So you can, for example, think about photonic crystals that are submerged or have some sort of like liquid host, or it doesn't have to be liquid, but it has to be a material that changes the refractive index much more notably compared to the solid or whatever that you're using. So I think this is a very interesting and new direction that we are actually following. One example that I also mentioned in the paper is basically using photorefractive materials in a matching host. For example, let's say you have a liquid, you have optical liquid, like ethyl salicylate or different types of liquids, and then you have a set of particles in that liquid, a solid particle that is photorefractive. So what happens is that now, because you have solid and liquid, although you won't see, you will see still at the matching point, you will see it as a uniform transparent medium. But when you shine light to this medium, you suddenly have like this giant, modulation of scattering, because the solid particles, which are photorefractive, are now going to stand out much more, compared to if you have just a sheet of crystal and you're trying to make, a modulation of refractive index on that surface. So I think it's a very, very interesting direction, and I hope scientists around the world can explore this direction more. And I think there's a lot of work that can be done. For example, looking into more anisotropic particles. Particles with like certain direction, like cylindrical particles and things like that. And the reason I think the Tyndall windows haven't been explored as much as Mie scattering or Rayleigh scattering is simply because when you have these kind of random particles, you have to either use like some sort of numerical simulation, or you have to use some sort of Monte Carlo simulations. So that's why I think it hasn't been touched as much, and it doesn't seem that liquid is always what the people in Photonics Society want to work with. So I think this mixture of solids and liquids together, I think it is definitely one good opportunity for the researchers to explore. Thanks.